regular expression, which is a contradiction. And we can just discharge all of these things. So in fact, all of the cases where we would have gotten stuck before are now completely discharged because they're not syntactically equal to our original regular expression. So now, in the case we get to where we actually have a star, well, now this is no longer contradictory, but because we have this equality as an assumption, we can use the injectivity of the constructor to get the fact that the star regular expression, this R double E prime, is in fact our original regular expression. So we're going to do inversion on it. And now, the good bit is, when we're matching the second string, we now know something about the regular expression we're matching against, namely it's a star, or star pattern, and it just falls right out. And a similar thing happens in the other case. I don't know why this is getting highlighted here. And we're done. So I guess the take-home message here is if ever you're doing a proof of induction in coq and you find yourself with not enough like you're getting into these cases that are obviously somehow contradictory, it might be worth going back and looking at the thing you did induction over and see if you're losing some bit of information when you're doing induction. And if you are, pull the remember tactic out of your bag of tricks and apply it, and it will to generalize the thing you're inducting over, and this will help. Again, this is one of those things, this is one of those sort of practical concerns that you only really recognize after you've been using coq for a little while. But I think the rule of thumb is if you're ever trying to do induction over, if you ever try and do induction over an inductively defined proposition or relation that has some concrete bit of information in it, you should probably step back and try and use the remember tactic, because that's sort of a bad smell. Rule of thumb. Okay. Okay, right. So, 1 second. I think what I'd like to do is skip. No, I'm going to cover the reflection chapter. This reflection bit's sort of important. Okay, so right. So we saw previously, I guess a couple of hours ago, that it's often helpful to relate a Boolean function or computation to some statement in prop for one of these decision procedures, right? We saw this with even b and this and the even inductive relation that we defined, and also this other formulation is a proposition of what it means to be even, right? Now, it turns out that if we want to now, once we've defined this decision procedure, right, we can judge whether or not a number is even or not by just evaluating the function, right? Or in this case, we can decide whether or not n is equal to m by saying, is the value of Beck-Nat true or false, right? So we can actually evaluate that, and we can say true. We can destruct, as we do here, Beck-Nat n equals nm, and that's going to give us two subcases, one for the case where this function is true, and one for the case where this function is false. Or the result of this, evaluating this function evaluates the false. But this is such a common paradigm where you have a proposition that is decided by some Boolean function that it's useful to not have to jump through as many hoops, because this gets a little bit painful where you actually have to destruct over the Boolean function, and then you do some rewriting with this thing exhibiting that it's equivalent to the proposition. It's such a common sort of reusable paradigm that it makes sense to come up with some more general methodology so you don't have to go through all these hoops every time, because it's annoying apparently. So here's how the trick for doing this. This is a trick you can use for anything. So let's look at it. So here's the idea. We're going to define an inductive proposition that's going to give us a better case analysis principle for a particular decision procedure. Okay, so instead of destructing or generating an equation that Beck-Nat equals true, and then we have to rewrite with this extra lemma. We're just going to use this induction, the reasoning principle that this inductive data type gives us to get the proposition directly. So we'll do a destruct and we'll immediately get n equals m, or n is even, or whatever the particular property that we want. So let's look at what this inductive data type definition looks like. Okay, so this says we're going to have some arbitrary proposition, and we're going to have it's going to be a relation on an arbitrary proposition, P, a Boolean, right? And yeah, that's it. And there are going to be two ways to construct this evidence of this data type. One is if the proposition is true, then this Boolean also has to be true. And if this proposition is false, well, yeah, this proposition is not true, then this Boolean is false. So what does this tell us? So this tells us if we have an assumption of the form reflect prop P true, we can conclude by inversion on that P. Similarly, if the bool is false, we can conclude not P. And to see why this is interesting, it's probably useful to just look at how it works in practice. So this says, well, actually just what I said before. B is true if and only if P holds. Implies that B reflects P. That is, B is a decision. We could think of it as being a decision procedure for this proposition. Okay. So what's interesting here? So here we go. We want to construct an element of this inductively defined proposition. So we'll just destruct B. Okay. And the case that B was true, right? There's only one way of building up reflect P true. It is the first constructor. And what does that need? We need to give it a proof of P. That's what this subgoal says. But we have as an assumption that B was true if and only if P holds, right? And of course, it's easy to show that P of true equals true. So we know P. And practically speaking, we're going to use this setoid rewrite tactic again, using on if and only if. What does this do? We're going to rewrite with H, and that's going to replace the left-hand side of this if and only if with the right-hand side and wherever we're rewriting. So we're going to get a goal of true equals true, and then we can just use reflexivity to discharge it. In the second case, we need to show it is not the case that P is, well, we need to show not P. So we're going to imply the constructor for the case where B was false, and now we need to show not P. Okay, but this is pretty easy to do because we have down here, I'm going to unfold that. We're going to need to, we need to show that P implies false. Okay, so let's intros P here. And now we can use the rewrite rule to replace this P right here with false equals true. Okay, so we can rewrite H in P. And we have now an assumption that false equals true, which is obviously a contradiction. So if we do inversion on P, we're done. Pretty cool. So we've shown that if we have some proof, if we can show that this Boolean reflects a particular proposition, we can construct evidence that that proposition is true using this reflect tactic. And the advantage of using this over the normal if and only if connective is that if we destruct a hypothesis or a lemma of the form reflect PB, we now have two cases. We have the case where B was true, and we get as an extra bit of information that P also holds as an assumption. And in the other case, we have B was false, in which case not P. So we get immediately, when we do case analysis on this, we either get P or we get not P, and we don't have to do any rewriting with this if statement. So it's helpful to see how this works in practice with a concrete example. So here's what we can do. We can show that BQ nat accurately reflects this proposition that n equals m. That is a correct decision procedure for it. So we're going to do intros. We apply if and only if reflect, which is what we showed before. And now we just need to show that the soundness of this decision procedure, which we proved previously, so we can rewrite with that, and we're done. Ooh, did that work? There's a lot of tricky things. Okay, so now we jumped through a bunch of hoops here. Let's see why it was actually useful. Okay, so now, in the case before, where we destructed on BEQ nat nm, right? We were destructing on this if statement right here. Now we can destruct this this reflected piece of evidence about of BEQ nat reflecting n of m. And what's going to happen? Well, first of all, it's going to replace all occurrences of BEQ nat here. There are going to be two cases, one where this is true, one where this is false. So we're going to replace all occurrences of this with true or false in those two subcases. And we also get an extra bit of information. Namely, we get p in the case that BEQ nat was true, in which case the proof proceeds normally, or we get a assumption that this proposition did not hold, so not p, or p n not equal to m, in which case the proof proceeds normally. So there were a couple of extra hoops we jumped through here, but the nice thing was this is like this pattern of destructing a decision procedure and then rewriting with the thing the proof that's showing this decision procedure sound, and then using that information in the proof is so common that this is actually a very nice way of sort of streamlining that process. So this is a little bit of proof engineering hackery that you might enjoy. So the higher order bit here is that, I said this before, for this simple example where we're just doing these equality tests, the reflection doesn't really seem to add that much, right? But using this reflect predicate often leads to much more shorter and clearer proof scripts, the larger proofs get, because all of the sort of smarts about how that proof proceeded is baked into this decision procedure that we built up. And it's also sort of embedded in reflect to cut out some extra examples. So this property was actually inspired by SS reflect, which you may have heard of. It's this coq library that's all built around this idea of using decision procedures and reflections for automating proofs and making them more tractable. And this library was used to prove the four-color theorem and the Feit-Thompson theorem quite successfully. And you can read a little bit more about SS reflect here. Yeah. So what is the takeaway bit about this discussion, this digression on reflection? It's that oftentimes, if you're working on with propositions that have decidable, that you can write a function that says yes or no, this is true or false. It's often convenient to do so, and then use that function when you're doing your proof developments. Okay. Are there any questions about reflection? Again, it's one of these things that I can tell you that it's useful. But once you start doing your own proofs and you start working with it, you'll see that this is actually a very powerful technique. And you'll have to take my word for it. And you'll only learn by doing, I'm afraid. Maybe I'm not afraid. Okay. If there aren't any questions, I'm going to move into some optional material here that should be pretty interesting. Okay. Okay, this is a cool bit here. So what I want to do for the next half an hour before lunch is dive a little bit more into this relationship between theorem proving and programming, which you may have heard of before. It's occasionally called the Curry-Howard correspondence. And the key insight here is that programming and proving in coq are the same thing, basically. Proving manipulates evidence or propositions, and builds propositions and destructs propositions in the same way that when we write a program, we destruct data and we build data, right? So there was a question earlier about what's the difference between inductively defined propositions and inductively defined data types, and I said there's there's no real difference, right? So, and that's right. If like the way we build up evidence or using these rules is in fact some form of data, right? These proof data trees very much can be thought of as data. What are propositions themselves? Well, they're just types, right? So the rules we use to build up a proof tree are the data, and the things they build up are propositions. And what characterizes data? Well, it's type, the type that it builds up. Okay, let's dive into this a little bit more deeply. Okay, so let's look at this definition of even that we gave before again. Okay, all right. Hopefully it still looks vaguely familiar. So suppose we took a slightly different way of looking at this definition, right? So when we see this colon, you could think of this as even has the type, nat arrow prop, right? Or you could read it as is a proof of that some natural number satisfies the proposition we're defining. So the constructor ev0, which has type ev0, you could read as ev0 is a proof that 0 is even, right? And it turns out this pun, the fact that you can interpret a type of a particular definition as also as a proof of some proposition, or its evidence for that proposition, is called the Curry-Howard correspondence. And it's this observation that there's this deep connection between proving a fact and programming, or writing an algorithm. And that proofs types are roughly equivalent, can be understood as being equivalent to a particular proposition or statement. And a proof can just be thought of some data value exhibiting a witness of that proposition. Yeah?
Was the paper?
What?
Was the paper you refer to?
What is the paper? So this is...
What's the title of the paper?
What is the title? I think it's propositions as types, yeah. So the Curry-Howard isomorphism as an idea has been around since the 60s. Like this is an old idea that is constantly rediscovered and reappreciated, and hopefully people in this room will appreciate it a little bit more after this lecture and after the summer school. But Phil Wadler has a really nice, this paper he has is a very nice essay sort of studying the history of this correspondence and some practical applications. So it's definitely worth reading. It's good. And hopefully other people in this room, if they've read it, can attest to that. Yeah. So, okay. And, right, many useful insights follow from this connection. So, right. I think I've been implicitly doing this as I walk through the definitions of this inductive data type, right? Where you can understand this constructor, you could understand it as a function, right? You could say EVSS is a function that you give me a natural number, and you give me some piece of data, EVN, and I will give you a new piece of data that that 2 plus n is EV, right? Another way to read it is that this is a function that you give me a natural number, and you give me a proof that that natural number is even, and I will give you a proof that 2 plus that natural number is also even, right? And I will give, this constructor builds the piece of evidence exhibiting that fact, which concretely realized is as a proof tree. So look at this example right here. So if we, after you write a theorem in coq, you state the theorem and you walk through the proof script applying some tactics. When it's done, you can use the print command to actually see the underlying proof object that was built up by calling these tactics, okay? So if we say print, it will actually exhibit for you the piece of data or evidence that it built up exhibiting the proposition that you stated in the initial statement of the theorem. And oftentimes this is quite gross, but here it's pretty simple. So if we look at this, what is the proof object we built up under the hood? What does the evidence look like? Well, it is probably what you expect. It just applies the